So in this session, I will explain the basic principles of I2C, which is Integrated Circuit Communication, and a closer look at I2C hardware of the STM32 microcontroller, and also I will show you how to interface the MPU 6050 accelerometer and gyroscope sensor module with STM32 Nucleo board using this I2C communication protocol. So for that, first we need to know what is I2C and its modes of operation. So I2C is a serial data communication protocol used to communicate between integrated circuits. So this protocol was created by Philips Semiconductor, now they call as NXP, back in 1982. So it is a synchronous half duplex multi-master multi-slave packet switched single-ended serial data communication protocol. And coming to this I2C signals and modes of operation, it is a two-wire protocol and they are called serial data and serial clock. Both data and clock are bidirectional lines which is connected to a positive voltage supply via pull-up resistor. So both the data and clock lines are held high when the bus is free. So the output stages of devices must have an open drain or open collector configuration. So the bus capacitance limits the number of interfaces connected to the buses. Okay, so actually there are four different I2C modes and they are standard mode, fast mode plus high speed mode. Okay, all the modes are downward compatible, means any device may be operated at a lower bus speed, but ultra fast mode devices are not compatible with previous versions because the bus is unidirectional. Okay, and then coming to the next thing. Okay, so in I2C, data transfer is always initiated by the master on the data line. So master first produces a start condition and after the start condition, the address phase follows. The address phase contains 8 bits. Okay, so the first 7 bits are the address of the slave and the remaining bits decides the read or write operation, something like that. So if the read or write bit is 0, that indicates the master will write the data to the slave, and if the bit is 1, that indicates the master will read data from the slave. So after sending the address, slave will compare the data with its own address. So if the address matches the slave, it will send an acknowledgement bit to the master and the master receives the acknowledgement bit. Once the master receives the acknowledgement bit, the master will start the read or write operation to the slave according to the read or write bit which is sent by the master earlier in the address space. Okay, so if the slave receives data, it will send the acknowledgement again, or if the master receives the data, then the master will send the acknowledgement again. If the master wants to send or receive more data, it can send or receive more data. If the master wants to end communication, it will generate a stop bit to close that communication. So please note that every byte put on a data line that must be 8 bits long and each byte must be followed by an acknowledgement bit. So data is transferred with the MSB first, most significant bit first. And now let's talk about the next thing, which is communication flow. In master mode, the I2C interface initiates a data transfer and generates the clock signal. And a serial data transfer always begins with the start condition and ends with the stop condition. Okay, so both start and stop condition are generated in the master mode by the software. And in the slave mode, the interface is capable of recognizing its own addresses. It can be 7-bit or 10-bit. And the general call address. So the general call address detection may be enabled or disabled by the software. Data and addresses are transferred as 8-bit bytes. MSB first. The first byte follow the start condition that contain the address, which is 1 in 7-bit mode, 2 in 10-bit mode, like that. The address is always transmitted in master mode. A ninth clock pulse follows the eighth clock cycle of a byte transfer, during which the receiver must send an acknowledgement to the transmitter. Okay. And coming to this MPU 6050 accelerometer and gyroscope sensor, this is how it actually looks like. So this is the world's first integrated 6-axis motion tracking device that combines 3-axis gyroscope, 3-axis accelerometer and a digital motion processor, all in a small 4x4x 0.9 mm package with its dedicated I2C sensor bus. It directly accepts input from the external 3-axis compass to provide a complete 9-axis motion fusion output. So this is a tracking device which is 6-axis integration, onboard motion fusion and runtime calibration firmware, and enable manufacturer to eliminate the costly and complex selection, qualification and like system level integration of discrete devices, guaranteeing optimal motion performance for consumers. Okay, and here I provide the circuit connection image. As we are using STM32 Nucleo board, we just need to connect MPU 6050 VCC to the STM32 Nucleo 3.3 ground to ground and take the clock pin and data pin. You can connect it to PB8, PB9, or in the board itself you will have like clock and data pin, right? So you can directly connect it to the pin also. Now we can go for the project setup. For that, let me open STM32Cube IDE, file, new STM32 project. No. Here I'm going to search like STM32F446RET6. Okay. So accelerometer and gyro. Okay, it's not valid, right? Gyro, let it be. Okay, so as usual the settings are very simple. Go to system core or CC, enable this and then go to connectivity, I2C 1, I2C, add I2C RX, go to DMA settings and then add TX, hit enter and then go for the same connectivity USR2 asynchronous, change this to PB8 and PB9, this is for data and this is for clock. Okay, and then go for clock config, change this to HSE, PLL clock, this to 8 and this to maximum frequency 72, hit enter and then save this to generate the code. Over here you will having like I2C, DMA, one is for I2C TX and RX and then UR. Okay, and then after this I'm going to define MPU 6050 address, which is 0 cross 68 left shift to 1. See, the last bit is for read or write bit. Okay, and then after this I'm going to define few more lines. So using define I'm going to give like register 0 cross 19 define gyro register 0 cross 1B, and then define axle config, this is not config, which is config register 0 cross 1C, define axle X out H register 0 cross 3B, and then define temp out H register 0 cross 4-1, and then define gyro X out H register, which is 0 cross 4-3, and then define PWR MGMT 1 register 0 cross 6B, and then define who I am 0 cross 75. So don't worry about all these addresses. This is just MPU 6050 register addresses. You can download the register map from the internet itself, right? So don't worry about this. And after this, unsigned integer 8_t receive data. Here I am going to just give an array like 6. C is spelling a mistake, right? So EI. Okay. So this array store the raw data of X, Y and Z axis of accelerometer, and then integer type 16_t axle X raw data. I'm going to initialize this with 0, and then same integer 16_t axle Y raw data. Also I'm going to initialize this with 0, integer 16_t axle Z raw data. Initialize this with 0, and then float type AX, AY and AZ. Okay, and after this I am going to write a function which is void PMU 6050. Okay, initialization. So inside I am going to pass the void. So inside I am going to write unsigned integer 8_t check value, and then send data, and after this haul I2C mem read. So instead I am going to pass H I2C MPU 6050 address, and then who I am, and then 1, and then address of check 1000. Okay, here I am going to write a condition. If check value which is 104 in the sense, inside I am going to write like send data which is equal to 0 cross 0 0, and then haul I2C mem write address of HI2C MPU 6050 address, comma PWR MGMT _1 register comma 1 comma and send data comma 1 comma 1000 and then send data which is equal to 0 cross 0 7. Okay, and after this again I'm going to give like hall I2C mem right, that is of h I2C we have to give 1. I forgot over here also 1 1. Okay, 1 comma MPU 6050 address SMPL RT DV register comma 1 comma address of send data 1000 and then now send data will be like 0 cross 0 0. Again hall I2C mem right. So inside address of h I2C 1 MPU 6050 address comma gyro config register send data comma 1 comma 1000. Now send data will be like 0 cross 0 0. Now again hall I2C mem right address of h I2C 1 MPU 6050 address comma axle config register comma 1 address of send data comma 1 comma 1000. Okay, so this is the function and now we can go for this void main function. Okay, so inside after all this I'm going to write a line like PMU 6050 initialization. I'm going to call that function and now inside this while I'm going to write few lines which is hall over here hall underscore I2C mem read address of h I2C 1 MPU 6050 okay address axle x out h register comma 1 comma receive data comma 6 comma 10 sorry 1000. Now axle x raw data which is equal to integer 16 underscore t and then receive data the array I'm going to give 0. I'm going to left shape this with 8 or receive data I'm going to give like 1. Okay, and this will be the overall thing. Now same axle y raw data which is equal to integer 16 underscore t inside receive data I'm going to pass 2 left shift to 8 or receive data I'm going to pass 3. Similar for axle z raw data which is equal to integer 16 underscore t receive data. Here I am going to pass 4, left shift to 8, receive data. I am going to pass 5, and after this ax, which is equal to axle x raw data. I am going to divide this by 16,384.0. Now a y, which is equal to axle y raw data. I am going to divide this by the same thing, 16,384.0. Now az, which is equal to axle z raw data divided by 16,384.0. Okay, and after all this I am going to end it with the delay of 1 second. So this is the program. So in the slide itself I have provided the screenshot of the connection. So make a connection, write the program, and burn your program into the board. You will get the output in the console box.